In section 6.7, we take the idea of equilibrium potential that we have been learning about in this chapter, and we apply it to the cells of the nervous system. We begin this discussion by mentioning that cells of the nervous system demonstrate what we refer to as excitability. So this means that they have the potential to change the charge that is found inside them very rapidly, and they accomplish this, of course, by altering their permeability to various ions that are found inside and outside the cell. There are some terms that we use to describe this change in charge that we observe in these cells. And so we have 4 terms down here at the bottom portion of this slide that we want to briefly discuss. Now, cells of the nervous system, as are all other cells for that matter, they maintain a negative charge inside them, as we know. And so we say that these cells are polarized. There's a difference in the charge found inside the cell and outside the cell. And so the first term that we see here is depolarize. And so, of course, as we've discussed, we're going to use the value -70 to describe the charge found inside the cells of the nervous system. It's a bit of an oversimplification, but that's a good common charge found inside the cells of the human nervous system. Now, some cells will vary, as we mentioned, but -70 is if we have to choose one value, then that's the best value. So that's the value our book has chosen. So the cell begins in a polarized state, and as we'll see momentarily, following excitation, it becomes depolarized. And so anything above -70 would represent depolarization, all the way up to a charge of 0, in which case the cell would be completely depolarized. Now, another possibility is this, that the cell goes all the way through the depolarizing state, and then it continues. And so at this point, it actually gains a positive charge. And so what we see is that we refer to this as an overshoot. The inside of the cell starts out as negative, completely depolarizes itself, and then goes through this overshoot and becomes positive. So we recall that the membrane potential of sodium is +60, and so that's why +60 appears on our graph, and an overshoot would represent an approach of the equilibrium potential of sodium. So we typically, what we'll observe is that cells don't make it all the way to +60, but that is why we observe overshoots in cells of the nervous system, because the equilibrium potential of sodium is +60 millivolts. And if we make the cell completely permeable to sodium, which we can't, but we can approach that by opening sodium channels, then we get into the positive territory. We get into positive territory. The next term, of course, is repolarization. So we go from somewhere up here above 0, probably +30 in the case of an action potential, all the way back down to -70. And so that, of course, represents this return to a polarized state, and therefore we call it repolarization. And then, excitingly, lastly, what we see is this, that we may actually overshoot the resting membrane potential, RMP, which is -70, and we call this hyperpolarization. And so this does actually occur in an action potential, as we'll see momentarily, when we return to the polarized state. And hyperpolarization is also observed in the neurons of most neurons of our nervous system, simply because the input from a presynaptic neuron may move the postsynaptic neuron further away as opposed to closer to an action potential. So in other words, there's a cell upstream, a presynaptic cell, that is destimulating. It is hyperpolarizing the postsynaptic cell. And we'll talk about the details of that later in our chapter. So for now, we just want to be familiar with our 4 terms that we have on this slide. We now turn our attention to graded potentials. Graded potentials are an interesting topic in physiology, and they are a small change in charge found inside the cell that's confined to a very a very small region of the cell membrane. Now, I'm going to go ahead and say this is in contrast to an action potential. An action potential is similar to a graded potential in that it's a change in charge, but it's a change in charge that spreads over a huge portion of the cell and moves very rapidly. And so essentially what we see is that there are particular characteristics that apply to graded potentials and to action potentials, and we want to make sure that we understand the differences between these. So we begin with graded potentials, we'll describe them, and then immediately we move on to action potentials. Now, what we notice is that this event is quite likely, although not absolutely, caused by chemical stimulus. And so what we see is that there's a ligand that binds to a ligand-gated ion channel in this particular case. And so I'm pointing with the little cursor here. If you look at the screen. And what we notice is that when this chemical stimulus binds, when this ligand binds, the ion channel opens, in this case, and ions flow through. In this case, we have an ion channel that's allowing a positive ion to move through the cell. So we see these happy little positively charged ions, cations, making their way through this ion channel and spreading out on the interior of the membrane. And so this is one of the characteristics that we know that is true of graded potentials. They only occur in a fairly limited area, and so these little cations are not going to move very far in either direction on the inside of the cell membrane. So what you see is that our book is illustrating the area close to the ion channel with a large positive charge, and then further away with a small one to indicate that there's a higher concentration of positive ions closer to the ion channel and a lower concentration further away from the ion channel there. So we notice, to be repetitive here, we notice that the positive charges are making their way along the inside of the membrane, spreading out a little bit, but not too far. Furthermore, we notice that on the exterior of the membrane, that as positively charged ions are pulled through the ion channel, that other positive ions move in the direction of that ion channel. And so we have this overall movement of positively charged ions from the exterior to the interior of the membrane in a graded potential. Now, we get to look at the characteristics of graded potentials on this particular slide. And these are nice graphs from our text that are found on page 132 and 152 and 153, it looks like, of chapter 6. And what we see is this. That graded potentials can occur in either a depolarizing or hyperpolarizing direction. And you would think to yourself, that makes perfect sense, because depending on whether a channel that allowed a cation or anion, a positively charged ion or a negatively charged ion to flow through, then you would either get a positive change in the membrane charge or a negative change as a result of the movement of the associated ions. So this is really important, and in fact, as you listen to this, the reason that you can listen to this and the reason that you can learn things, the reason you can think, all of this ties very closely to these graded potentials. I guess it'd be good to go ahead and say this. Graded potentials lead to action potentials. Graded potentials lead to action potentials in a manner that we'll describe in perfect detail. It's fairly simple, but we'll certainly go over it in this particular chapter, but that's the importance of graded potentials. And so they're constantly occurring in those 86 billion neurons that are present within your brain. And it's very important that they can be depolarizing or hyperpolarizing, because a depolarizing graded potential takes you closer to an action potential, makes it more likely that a cell will initiate an action potential, whereas, of course, a hyperpolarizing graded potential makes it less likely that post-synaptic cell will initiate an action potential. Okay, point number 2. In the case of graded potentials, magnitude varies greatly. And so you may say, well, I don't understand. Why does that matter? And that would be a good question, but interestingly, in the case of action potentials, there is no variation in size. An action potential is an action potential period. There's no big action potential, there's no small action potential, there's just an action potential, as we'll see soon. This is not true of graded potentials, and in fact, in the case of graded potentials, because their purpose is to either take a cell closer to or further away from an action potential, the size of a graded potential is tremendously important in terms of its impact on the overall physiology of the organism. So, let's see. Let's take a look at our graph down here on the left-hand side. I'm using the pointer to the cursor to point. So if we look at part A, we see that we have a depolarizing graded potential. We see a little blip there following the stimulus where the charge goes up and of course taking you closer to zero. Therefore, it's depolarizing because it's reducing the difference between the charge on the inside and outside of the neuron. And then down here we have a hyperpolarizing graded potential because of course it takes you below negative 70 and further away. It increases the difference in charge on the inside and outside of the cell. Next we look at B. And so here we see that we can indeed have a small action potential following, I misspoke. A small graded potential, not true of action potentials as we mentioned, but a small graded potential following a weak stimulus, or we could have a strong graded potential, a large graded potential, I guess we should say, following a strong stimulus. And the last point that we want to make here is this, on this slide at least. Graded potentials are decremental. This means that they diminish from the site of initiation. And so this is illustrated in several points on this slide in figures taken from our text. First, let's go to the figure found in the upper right-hand portion of our screen. So here we have the initial site of depolarization, that in this case it's a depolarizing graded potential. And what we notice is that we have a good bit of charge found close to that site, and then a little less as we move a little further away, and a little less, and a little less, and a little less, and a little less. So ultimately, the current flows within the neuron, and the graded potential does spread out, as we saw on that previous slide. But it does go away. It does dissipate. And so as it turns out, neurons are not terrific conductors of electricity over long distances, especially in the absence of myelin. And we'll talk about that when we talk about action potentials. Neurons are capable of sending signals very rapidly from one part of the body to another, but they don't do that via the method that an electrical wire would use. And so, of course, copper, you add electricity to one side and it shoots it down the wire. That's not what happens in our neurons, as you know. And so an action potential, which is a long-distance signal in the nervous system, requires regeneration over every tiny little increment. So that's what we see there in the upper right-hand portion of our screen. Graded potentials are decremental. We also see this illustrated down in part C, in the lower left-hand portion of our screen. So we see the stimulus, and we measure the graded potential at the site of the stimulus, and it's quite large. But then, if we go 1 millimeter away from the stimulus site and we measure it, then it's much, much smaller. This graph may be a little bit confusing, but do keep in mind that time is on the x-axis, not distance, and so you have to imagine that the graded potential being measured at these different distances, but the portion of this graph that's found further to the left is measuring at the site of the stimulus. The portion found to the right is measuring 1 millimeter away, so as we saw in the upper right-hand portion of our screen, in this diagram, the signal, the change in charge, has largely dissipated at this point because graded potentials are decremental. And then finally, this may be getting a little overboard, but your book does provide you, going a little overboard, your book does provide you with one more illustration of this. And so what we see are two of the phenomena that we have just discussed illustrated here in this particular diagram. Number one, we see that we can have a small or large graded potential depending on the strength of the stimulus. Number two, we see the decremental nature of graded potentials. And so that we see in both cases, even in the case of the high intensity graded potential, the large graded potential, then it does dissipate completely within a fairly close proximity of the initial stimulus. Excitingly, at this point, we get to action potentials. And so action potentials, of course, are probably the most important topic in all of the study of the physiology of the nervous system. And we'll talk about them in different steps here. This is an initial slide that shows us the important channels that are at least the main ones that are involved in an action potential. So we're going to contrast an action potential to a graded potential, what we just got done discussing in the previous slides. And action potentials are large changes in membrane potential. And so we go from a polarized state of negative 70 to a depolarized state, and then we go all the way up to positive 30 in the case of an action potential. And as I mentioned a few moments ago, action potentials are not big or small, but rather they are just action potentials. We cannot have a big action potential and a small action potential. They're all exactly the same size. Action potentials are also very rapid. They move very quickly. They don't last very long. And you can move a lot of them along an axon in a very short period of time. So I think that we've made this clear, and you probably already know this regardless, but an action potential is a charge that moves down an axon. And so imagine stubbing your toe. Hopefully not very, very hard, but you experience a sensation as a result of hitting your toe gently against the wall. So that sensation has to make its way all the way up your leg, then all the way up your spinal cord to your brain before you experience that, before you know that your toe has touched something. And so that's, of course, accomplished by these action potentials that move very rapidly up a series of neurons from that toe all the way up to your brain. It's also interesting. What we'll see is this. This is perhaps best, it might be best to wait till later to bring this up, but let's go ahead and mention it. So we see that this statement, several hundred action potentials per second on this slide. Well, interestingly, because all action potentials are exactly the same slide, the intensity of a stimulus, whether it's painful or pleasurable or whatever that stimulus is coded for by the frequency, not the magnitude of the action potentials. It would, of course, be impossible to code for the intensity of a stimulus using the magnitude of an action potential because they're all the same size. And so if something hurts a lot, well, you're getting a lot of action potentials that are headed back to your brain. If something doesn't hurt very much, then it's a lower frequency of action potentials. So action potentials obviously are, as that next bullet point says here, important in long-distance communication. Now, how do they work? Well, to understand how action potentials work, we, of course, need to have an understanding of the ion channels that are allowing these transient changes in membrane, in the charge on either side of the membrane as an action potential passes. So there are two that we really want to be familiar with to understand how an action potential works. The first one is a sodium channel, and the second one is a potassium channel. Now, you'll recall from earlier sections of this chapter that we maintain the cells of our nervous system maintain sodium at a very high concentration outside the neuron and potassium at a high concentration inside the neuron. This provides the opportunity to open a sodium channel and let sodium flow in, and that can be accomplished very, very rapidly. Now, it would take much more time to pump sodium from one side to the other. And in fact, as you know, with the sodium-potassium pump, sodium is pumped constantly from one side to the other, but it would be very difficult to transmit a signal within a few milliseconds. Well, the things that we do in lab will be measured in milliseconds, and beginning with this upcoming lab on the human neurons. And so it would be very difficult to do that if you had to pump something. You really need to let something that has a very high concentration difference flow to accomplish a signal that moves that quickly. So let's do the sodium channel first, and here are some adjectives describing the sodium channel. It's fast. The sodium channels work very, very quickly. Again, milliseconds. Think milliseconds. Take a second, divide it into 1,000 parts. That's how quickly these events are occurring that we're now discussing. So what happens is, if we look at the blue rectangle on our slide, here, where I'm pointing right now, the left-handmost diagram here, the sodium channel is closed. Here, the sodium channel opens for reasons we'll soon describe, and sodium flows through. And then here, interestingly, this inactivation gate, which is often described as a ball and chain, it's of course a protein structure, comes around and it plugs the sodium channel. And so this is essential to the overall functioning of the action potential. So in other words, to sum it up, the sodium channel opens and then it's inactivated. It hasn't closed. Note that we're not saying that it closed, but it is inactivated, meaning it can't push anymore, can't allow any more sodium ions to flow through, and all this happens very, very quickly. Number 2, the potassium channels. So if we look at the red rectangle down here, we see the potassium channels, and what we see is this, that the potassium channel is either closed or open. And you'll notice that the arrow is headed in the opposite direction, because in this case, we're allowing potassium ions to flow from the inside of the cell to the outside of the cell. And as you've guessed or already know, or can see using this black arrow that's found on our screen, this is a part of a repolarization. Repolarization. So we're going back to the repolarized state because the potassium ions are flowing out of the cell. The sodium provides the depolarization, and the potassium ions provide the majority of the repolarization. Good. Now we'll go on and talk about the steps of an action potential. At this point in our chapter, we get to look at the mechanism by which an action potential occurs. So essentially what we have is this initial depolarization after we've reached the critical threshold. We'll build on this idea of critical threshold in just a moment. After we have reached the critical threshold, we have this positive feedback that allows more and more of these sodium channels to open, allowing sodium to rush into the cell and take us away from the resting membrane potential of -70 and towards that equilibrium potential of sodium, which, as you know, is +60. We never quite get there because what's going to happen is those inactivation gates that we saw on the previous slide come into play. They block the movement of sodium, and then the slower, as we also saw in the previous slide, potassium channels activate. And this helps to repolarize, actually causes the repolarization of the membrane, taking us through a brief period of hyperpolarization and then back to the resting membrane potential. So we want to look at these events in more detail, and we'll take a look at the figure that's shown in the bottom left-hand side of our slide in just a moment. But before we do that, let's take a look at the one that's found in the upper right-hand or middle right-hand portion of our slide. And so what we see here is this whole deal that we're discussing, the action potential, is a result of these changes in the permeability of the membrane of the neuron to first sodium and then potassium, and it takes us either closer to the equilibrium potential of first the sodium ion and then the potassium ion. The equilibrium potential of sodium, as you know from our earlier discussions in this chapter, is +60. Equilibrium potential for potassium is, of course, -90, as you realize. And so it's all about this whole thing that we're going to be discussing. The action potential is the result of changes in permeability of the neuron, very transient changes, as you can see, because on the x-axis, here we have milliseconds, believe it or not. So time in milliseconds. And so what we notice is that first, the permeability for sodium goes up tremendously. And this is a nice picture from our text. So we see this graph corresponding to the states of the ion channel up at the top of the graph. So you can see the sodium ion channels completely open there at the peak, and then you can see the inactivation gate moving into place there if you're following the cursor as I move it on the screen here. And then look at the precipitous drop that occurs in permeability to sodium that follows the movement of that protein gate, which is going to block the sodium channel. And then, so this is important and something we haven't talked about so far. Look what happens to the far right here. We notice that the sodium ion channel does close as a result of the change in voltage that's been brought about by potassium. But you'll notice the difference here. So sodium ion channels cannot go through either where I'm pointing now when the inactivation gate is in place or now when the channel is closed, but we do go through those two steps in very close proximity there, which leads to the changes that we see in the graph of sodium permeability in the neuron. Now let's look at the potassium gates. And so as you already know, potassium gates are faster or slower, and the answer is slower than the sodium gates. And so what we see is that the sodium ion channels open here, allowing a tremendous amount of, I'm really sorry, I'm using the wrong term. Let's look at the potassium channels. So the potassium channels open here. The potassium channels are slower. And so we have this tremendous efflux, this movement of potassium out of the cell. And we can see that illustrated down here as this red line goes up, indicating an increase in the relative permeability of potassium in the neuron. And as the potassium leaves, of course, it's a positively charged ion leaving, so the charge inside the cell drops dramatically. We can see that if we go back over here to the figure on the left-hand side of our slide. And so we see the charge inside the cell dropping dramatically as the positively charged potassium ions leave the cell. Okay, having done that, let's go to the next slide, because in the next slide I've simply taken this figure that I'm circling here in the lower left-hand side of our slide and expanded it. Here we are. So what we want to do here is to talk about the steps that occur in each of these at each of these points during an action potential. These are very valuable figures that are frequently presented by your text, and they can be kind of laborious, having as many as perhaps 30 little steps in the case of some of the cardiac events. But it's really important to be able to work your way through these and understand. You don't have to certainly be able to restate what the book says verbatim, but be able to explain in your own words what's happening at each step. So let's do that together on this particular slide. We begin at number 1, and so at number 1, really nothing is happening. We see that both the sodium ion channels and the potassium ion channels, if you follow the cursor on the screen as I move it, are closed, and the neuron is at a resting membrane potential of -70. None of that's surprising. Now, what has to happen here is that we have to reach this threshold voltage, also known as the threshold potential. We'll talk more about that actually on the next slide, but that's what's happening at number 2. It's referred to as a threshold voltage, and in this case it's about -55 millivolts. It's referred to as a threshold voltage because that's the voltage required to open the sodium channels. It's a little bit disturbing to me that this open sodium channel is not directly under number 2 there, but what we notice is when we get to number 2, these voltage-gated sodium channels do open in response to the change in voltage, and so this allows a tremendous influx of sodium into the cell. You may ask the question, and this will be a good question, why does the charge go up to the threshold voltage if the voltage-gated sodium channels are not having an impact? It's a good question, and that's one that we'll address very shortly here, but it'll probably be more efficient and less confusing if we don't address it at the moment. So once we get to the threshold voltage, the sodium channels open, and number 3 represents this tremendous increase in charge inside the cell as we shoot upwards, going all the way to 0, and then passing that, shooting towards the resting membrane potential for sodium, the equilibrium potential for sodium, which, as you know, is +60. But then we reach number 4. So number 4 represents as far as we're going to get as far as our progress towards the equilibrium potential for sodium, +60. We don't get there, as you notice. We do get to +30. We only make our way to +30 because of the inactivation gates. This protein apparatus swings it around and plugs this open sodium channel, preventing the further entry of sodium into the cell. So this is essentially a dead end for the cell. No more sodium can make it in, so we're stopped at that particular point. Now, you already understand that the potassium channels are much slower than the sodium channels. And so it's not until number 4 that the potassium channels actually open. And this is when the sodium channels, this is not much time in absolute sense, but relatively speaking, then it is a good deal of time. The sodium channels have been open, and then they have been inactivated before the potassium channels even open. Now, once the potassium channels open, we ask ourselves, does that allow potassium to go inside the cell or out? And of course, the answer is out, because we remember that potassium is maintained at very high concentrations inside the cell. So we have this tremendous efflux of potassium out of the cell, causing the drop. This is number 5, drop. We go down below the threshold voltage, following the cursor on the screen. We make our way back to the resting membrane potential, -70, and then we even drop below that, engaging in some hyperpolarization, as we mentioned earlier in our discussion here. So we have dropped below the resting membrane potential, -70 of the cell, as a result of the fact that these potassium channels are fairly slow, both to open and to close. And so these are voltage-gated channels, and they should be closing. In other words, their opening is triggered by the positive charge inside the cell. They should be closing as we get back to the resting membrane potential, because, of course, they were closed to begin with, and that's the nature of, they are proteins, and that's the nature of those proteins, how they respond to charge. But it takes them a while to do that. So by the time they have closed, enough potassium has left to drop below the resting membrane potential. And then, once all those potassium channels have closed, which is what we see over here, then the sodium-potassium pumps kick in, and we restore that concentration of sodium and potassium on opposite sides of the membrane, taking us right back to a resting membrane potential of -70. We now return to this idea of threshold voltage. And it's a very important idea in neurophysiology, maybe one of the most important ideas. And what we see is this, that the threshold voltage is typically 15 millivolts less than the resting membrane potential. We've already said that in our case, we're going to assign a value of -70 as the resting membrane potential. And so, of course, that means that in our case, the threshold stimuli will be about -55, which is 15 millivolts higher than the resting membrane potential. Now, it's only a threshold stimulus for this particular reason. That is the voltage at which these voltage-gated sodium channels open. And so this means that if you reach the threshold stimuli, the threshold voltage, then you open sodium channels. But if you don't, then nothing happens. Now, we're tying, hopefully, we are, and hopefully this makes sense, we're tying a couple different concepts here together. The threshold stimuli is something that is created by a graded potential. So a graded potential, the question that you want to ask regarding the graded potentials that we just discussed a few moments ago in this chapter, the question that you should ask is, are these graded potentials collectively sufficient to reach threshold? And if they don't reach threshold, then it's like they never happened. So let's look at the graph that our book provides to see an illustration of this. Now, on the bottom of this graph, or figure, 2 graphs perhaps, we have a very small stimulus located here on the left-hand side that I'm pointing to with the cursor. That gives us a very small graded potential, which doesn't come anywhere close to reaching the threshold potential of -55. And then we apply a slightly stronger stimulus, and we get a much larger graded potential. And then you can see that as we go up, we have 3, 1, 2, 3, and they're offset a little bit. So here's the third one, and you can see here's the response of the membrane in the form of a graded potential to this third stimulus, but still nothing happens. And so you could, if you want to put this into practical terms, think about this. So if this is occurring somewhere, for instance, on your skin, then you would never know that something was touching you there. Perhaps the light, a very small bug walking across your skin or something of that nature. It's generating these graded potentials, but they're not sufficient to create action potentials in sensory neurons, and so you're just unaware that anything is occurring. Now, the fourth stimulus that we have here is significant, and so this is a threshold stimulus because it creates a graded potential that takes us just barely above the threshold voltage. And so once we go above the threshold voltage, then the voltage-gated sodium channels open, and we fire an action potential. Look at that. And so that's the whole idea here. Do we get to the threshold voltage or do we not? Now, interestingly, as we mentioned previously, action potentials are all or none. There's not a big action potential or a small action potential. There's just an action potential. They always go from negative 70 up to positive 30, a little bit of hyperpolarization, and back to negative 70. There's no other options there. So this means that even though the stimulus, let's see, 1, 2, 3, 4, 5, that's a point here, stimulus 6 and stimulus 7 are increasing in strength every time, the response of the neuron, therefore the response of the body, you could say, is exactly the same. And so there's no way you could distinguish stimulus number 5 from stimulus number 7, even though, or 4 from 7 for that matter, even though 7 is a great deal, relatively speaking, more intense than is 4. So we'll talk about some different mechanisms the body uses to distinguish one stimulus from another and the intensity of stimuli as we go forward. But we already mentioned that the most basic idea is this, that the intensity of a stimulus is coded for by the frequency of action potentials, not the magnitude, because that would be impossible. And so we see that point illustrated again over here in our notes. Bullet point number 3, action potentials are all or none. You may like the firing a gun analogy. And so, of course, when you fire a gun, you pull the trigger and the bullet leaves, and the speed at which the bullet leaves has nothing to do with how vigorously you pull the trigger. And so that's a frequently used analogy, one that your book uses, but it's probably a good analogy describing to us the nature of action potentials. Lastly, what we see is this, that if you want to stop the sensation in a certain part of the body, what you need to do is stop the generation of these action potentials. And so that can be accomplished by using a drug that physically serves as a block for these voltage-gated sodium channels. Novocaine and lidocaine are such drugs. They interact with the body in a very valuable way because they serve as a temporary, you wouldn't want a permanent plug, they serve as a temporary plug on these voltage-gated sodium channels, and therefore they temporarily suspend the movement of action potentials down neurons, including neurons that carry pain, which of course is a valuable thing if you need to perform surgery, dental surgery, or otherwise in a very localized area of the body. It's also interesting to note that nature has come up with similar toxins, and in some cases that we have harnessed and used. Not sure about this particular toxin, but interestingly, Tetrodotoxin, which is produced by the friendly pufferfish that we see there, works in a similar manner to Novocaine. It physically blocks those sodium ion channels. However, it's much more potent and spreads through the body much more rapidly, and so it can be very deadly. Interestingly, the pufferfish is a delicacy, and considered a delicacy in many parts of the world. It's very expensive, but it's also very dangerous to eat because this tetrodotoxin is found within the pufferfish, and if it's not prepared correctly, it can be a fatal error. So interestingly, only chefs that have a license to do so can prepare pufferfish, making a dish referred to as fugu. We've now finished discussing the events of an action potential and the importance of threshold stimuli. So this is the last topic on this particular slide, refractory periods, that we need to cover before we can have an understanding of how an action potential moves down an axon. And so this is a fairly simple idea, but one that we need to glance at because it does dictate the way an action potential behaves in a neuron. What we see is this, that neurons go through, actually sections of neurons go through these things referred to as refractory periods. And these refractory periods are either absolute or relative, depending on the point in time at which we find a particular section of a neuron. The refractory periods are a result of the nature of the voltage-gated sodium channels. The potassium channels are impacting the sodium channels in this case, but it is the sodium channels that actually cause this refractory period. So if we look at our graph here, then we can understand what happens in a refractory period. If we start at the left-hand side, what we see is this, that on the bottom we have our stimuli, and on the top we have our response of the neuron as measured in the change in charge of the membrane potential, in other words. So we first have a small stimuli that takes us past threshold, so it takes us past the negative 55 millivolts required for the sodium gates to open. We undergo an action potential, which is everything that we just learned. Nothing surprising there. And at this point, we are in what's called the absolute refractory period. This means, as your book is illustrating here, that we can apply as strong a stimulus as we want to the neuron, and we get absolutely no response. And so this tall black bar here indicates a very strong stimulus, but then the little smaller bars above it indicate we could go as high up as we wanted, and we still would not get any response. The reason for this is that at this particular point, the inactivation gate is located in that sodium channel, and so it's impossible for any additional sodium ions to flow through that particular channel. So that's the absolute refractory period. Then, if we move on just a few milliseconds down the x-axis here, what we see is this, that we enter something called the relative refractory period. This means we can apply a fairly strong stimulus, as I think you'll agree. Look at the height of the red bar here representing the intensity of the stimulus. And if we do that, we do get an action potential, but the action potential is a bit less in magnitude than we would otherwise. So this is the one exception in all of neurophysiology in which we have a difference in size of an action potential. And it's a little bit misleading because it is a lesser in magnitude, but it's a result of this. So what's happening is that potassium, as you know, is rushing out of the cell at this particular time, causing the cell to repolarize. And so what we're illustrating here at the beginning of the relative refractory period is that we can stimulate another action potential, but we have to get back to the threshold voltage of negative 55. That's going to be hard to do with all this potassium rushing out because we have to overcome, we have to supply a great deal of positive charge in the cell to counteract all the positive charge in the form of potassium that's rushing out of the cell. But if we do that, then we can, of course, once again, as you would agree, cause those sodium channels to open, and we can allow sodium to rush into the cell. The reason for the lessened amplitude of these action potentials during the relative refractory period is obviously, as we've been discussing, the movement of potassium that's exiting the cell. So the behavior of the sodium gates is identical, but the result is lessened as a result of the fact that you have charge that's rushing in the opposite direction. Sodium is rushing in, potassium is rushing out. Now, as you would imagine, we go through this progression where a larger and larger number of these potassium channels close. And so here we're in this hyperpolarized region, and then here we're coming out of the hyperpolarized region. So we don't have to apply quite as strong a stimulus here to get to the threshold voltage. And then here, this is towards the end of the relative refractory period. You know, this is not much above just a typical stimulus that would take us to threshold. And then we're out of the relative refractory period here if you're following the cursor, and so we're back to normal. So this explains this idea of a refractory period. The absolute, which is caused by the inactivation gate, the relative, which is caused by this movement of potassium ions. And so this is important. If we look over at bullet point number 3 on our slide, this is important because this gives us the absolute limit of action potentials that can travel down a neuron. We already mentioned that stimulus is coded by frequency in the case of neurons, and so we're now saying there is a limit to the absolute maximum number of action potentials that we can send down a neuron, and therefore we would assume there's a limit to the absolute amount of, for instance, pain that could be experienced in a certain region of the body. And this would be true, but we also have to consider the idea of recruitment, that additional neurons can carry a signal, and so the more neurons that are recruited, the stronger the stimulus will be. This also determines the direction of an action potential, as I think is probably already clear, or at least will become clear on the next slide. The action potential cannot move backwards because of the mostly absolute and then perhaps the early part of the relative refractory period, because those sodium channels are inactivated for a brief period of time, and by the time they're active again, the action potential is gone on down the axon. At this point, we get to tie together several of these topics that we've just finished talking about, most notably perhaps threshold voltage, the refractory periods, and then the steps that occur within an action potential. And of course, we're also building upon the equilibrium potentials, the ions that we talked about earlier in this particular chapter. So on this slide, we see an illustration of how an action potential moves down an axon. And we'll start in part A here, and what we see is this, that we have reached threshold voltage in this critical area of the axon. So if you follow the cursor, this of course is the cell body, this is the axon, and then this is something referred to as the Axon Hillock. And so at this Axon Hillock, this is the very important region of the axon, because this is the region at which we will or will not reach this magical negative 55 voltage, which is known as the threshold voltage. We'll build on that idea a little bit in just the next slide here, but you already understand that neurons are in the business of integrating information. So they receive input, as we've said, from as many as 1,000 presynaptic neurons. And how they respond is dependent upon the voltage that is obtained or eventually achieved here in this axon hillock. So in our diagram, we have achieved the threshold voltage, we have fired an action potential, and what happens is this, that all the steps we just learned about occur in this area that's shaded in blue on our screen. We have the little numbers that are located under here. And what we notice is that the sodium is rushing into the cell at this particular point, and it's turning the inside of the cell from negative 70 eventually to positive 30. And so if we look up above the graph here in part A, we can see that charge rushing upwards towards the equilibrium potential for sodium, which is positive 60, as you know, as we already understand. And then as we look over to the next two segments of the axon, we see that we see two things that are of note. So in this adjacent segment, look what's happening. The voltage in here is starting to go up just a little bit. So what we're saying is that the positive charges that are coming in here are impacting the area that's found just to the right here, which is really essential. It's everything in terms of understanding how an axon propagates itself. But as we've also already said, these neurons are fairly poor conductors of electricity if they don't have these ion gates that are conducting the electricity for them. So just within the axon itself, these charges don't spread too far. You remember the decremental nature of, for instance, a graded potential. So it's only going to move a little bit. That positive charge just moves a little bit down the axon. And that means that if we look over to section number 3 here, then there's no change in charge at this point. So let's go to B. We jump down here to B, and what we notice is this. Then look at what's happened. We have transitioned what was in figure A on the far left has now moved over in figure B to the middle. So this positively charged region of the axon is now midway between what's shown as the beginning and then as far as we can see at least, maybe not the end of the axon, but far down the axon. So it's right in the middle at this point. What was charged a moment ago, what was positively charged inside the neuron a moment ago, if you follow the cursor, has now gone back to negative. And so this is, of course, what you understand. We have reached that positive 30. We're cascading back down towards the resting membrane potential as a result of the opening of the potassium channels and the efflux of the positively charged potassium out of the cell. And this is important, we're going through those refractory periods that we talked about on the previous slide. So we'd be in the absolute refractory period right here where the cursor is, adjacent to the positively charged region, and the relative one over here. And so this is extremely important, and I think this is the most important idea of this whole slide, is if you understand this, then everything is fine. The action potential cannot go backwards because of these refractory periods. The positive charge is spreading out, just as our book tells us, this far to the left, this far to the right. But as it spreads out to the left here, it would cause these sodium channels to open if it weren't for the refractory period. So this part of the axon is out of order for the moment. This means that the action potential can only move forward because this part, if you follow the cursor, the one to the right, this part of the axon is not, of course, in a refractory period, but these sodium ion channels are certainly ready to open. And so what's going to happen, of course, is if we go down to C, that they do open, the positively charged sodium rushes in, and the action potential propagates in this particular manner. So I think it's important to understand that the action potential is something like a wave at a large sporting event, like a football game. So you've probably seen this or can imagine what it looks like. It's that thing that occurs, of course, when everyone gets kind of looks around and they all of a sudden jump up as this so-called wave moves around a stadium. If you've never seen it, Google it and take a look at it. So the wave is a real entity. It does move around the stadium, but it's not something that moves horizontally, cruising around the stadium. You couldn't grasp the wave or ride on it. Rather, it's just a change in state of the people that are seated all around the stadium. Likewise, an action potential is just a change in state of these ion channels along the axon, allowing a temporary change in charge of the axon. So it is a real thing. It's a change in charge that moves along the axon, but there's nothing that, once you get to the end, that was carried from the beginning, which is an interesting idea. So this is how 100% of our neurons function, no exceptions here. They're all about conducting action potentials. There are all sorts of neurons, all sorts of shapes, sizes, and all kinds of ion channels and receptors and so forth, but they all participate. It's all about generating action potentials. So if we understand this, then we're in great shape as far as our beginning discussion of the nervous system goes here. We also want to mention this, the last bullet point here, that there are two things that impact the speed at which an action potential is conducted down a axon. The first is diameter. And so larger diameter axons are definitely faster. And so larger diameter axons are found in, for instance, the large motor neurons that go to our quadriceps. Those conduct signals relatively rapidly. Smaller diameter neurons, such as those that are associated with sensory roles, for instance, conduct impulses much more slowly. Typically, those are shorter axons as well. Lastly, the last thing that impacts speed is myelin. So to discuss myelin, of course we have discussed myelin to some extent, but to wrap up that discussion, we go to the next slide. Here we see the impact of myelin on the speed at which an action potential is propagated down an axon. So it'd be a good idea to review at this point and think about the cells that provide myelin. We remember that in the central nervous system, it's the oligodendrocytes that reach out and myelinate a number of adjacent axons, that structure that somewhat resembles an octopus perhaps, with those arms that reach out and form the myelin. And then in the peripheral nervous system, we have the Schwann cells, which are perhaps depicted here. It could be either one, I suppose. But to me, it looks more like Schwann cells that are a cell in and of itself, with the cell body and nucleus actually part of the cell that's wrapped around a number of times the axon itself. So what we see is that this manner in which myelin impacts the speed of conduction is fairly simple. If myelin is present, it leads to something referred to as saltatory, which means to leap conduction. And what we notice is that we have, first, if we follow the cursor, a region of myelin, a myelinated region of the axon, and then we have an open region where there is no myelin. We call the open region a node of Ranvier. So we have myelin, node, myelin, node, myelin, node. The nodes of Ranvier, interestingly, are the only points at which the action potential must be regenerated. We've already said that these axons are fairly poor conductors of electricity. But if you wrap myelin around them, The lipid-rich myelin provides a great insulator for these charges. This means that if we depolarize the cell here by conducting an action potential, then that charge is sufficient to make its way all the way through this myelinated region to the next node of Ranvier, where it depolarizes these cells to threshold voltage, causing these, these proteins, these ion channels, to threshold voltage, causing them to open and the sodium to rush in, and then furthermore, it makes its way down the axon to here, causing these sodium channels to reach threshold voltage, and so forth. And so this means that the signal travels very, very rapidly, because instead of having to regenerate itself, if you're following the cursor, at every little point, here, 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 and here, it just has to occur here, and then it jumps to here, and then it occurs here, and jumps to here, and so forth, all the way down the axon. And this is a big deal. So if we look at our stats up here on our slide, we see that in small non-myelinated axons, we have speeds that are typically in the range of 0.5 meters per second, which would be equivalent to 1 mile an hour, slower than you would walk. And so if you're going to go from the brain to the toe in a human body, this would take about 4 seconds, which is a long time. I think we'd agree with these little non-myelinated axons. Now, it's safe to say these are not the axons that the body uses to get signals, at least primarily from the heel all the way up to the brain. So what we see is that in the body, more myelinated axons are used to transmit signals long distances from one part to another. And in these large myelinated axons, we can achieve speeds of 100 meters per second, which is 225 miles per hour in these very large myelinated axons. So at this speed, it would take 0.2 seconds to get from the heel all the way up to the base of the brain. Lastly, we want to try to loop back and make sure that we're comfortable with the way that these action potentials are initiated. And we want to add one term to our vocabulary at this point, the receptor potential. And so a receptor potential is something you already understand. We just haven't used that word yet. A receptor potential is a type of graded potential that's produced by sensory neurons. And so what we see is this. Imagine you are pushing on the desk in front of you. And as you push on that desk, you're causing the compression of these very small sensory receptors, and you compress them enough that they generate an action potential. That action potential then makes its way back to your brain and tells you that you're touching something. And so that we refer to those as receptor potentials. Those occur in all the sensory organs of our body, our eyes, our ears, our skin, of course, and we have all sorts of ones that, as we'll see in a future chapter, are specialized for particular modalities. In other words, heat, cold, pressure, pain, and so forth. Next, and perhaps more importantly, we want to discuss synaptic potentials. And so synaptic potentials are another type of graded potential, but in this case, they're generated by synaptic input. This is illustrated on our screen, and perhaps is the most important idea that we see, at least on the screen, and one of the most important ideas in neurophysiology. So here we have, if you follow the cursor, the post-synaptic cell, and we have 1, 2, 3, 4 presynaptic cells that are having input, in this case, on the post-synaptic cell. This one, and this one, the green, the blue, and the dark green up here, cells are having a positive impact. In other words, they are creating something referred to as excitatory postsynaptic potentials, EPSPs, if you see the little abbreviation on our screen, excitatory postsynaptic potentials. And that's what the little upwards bend, and that represents an upwards bend in the resting membrane potential. That's what we see next to each of those. So the more input we have from those, the higher the charge gets inside the cell. We have one presynaptic cell that is hyperpolarizing, and so it's providing us with what's called an inhibitory postsynaptic potential, an IPSP. And so the bottom line is that all these neurons are having input, and depending on which which ones have more input, we either will or will not reach the negative 55 millivolt threshold voltage here in this trigger zone that is the Axon Hillock. As we mentioned, the Axon Hillock, of course, this is the axon that I'm pointing to here, and we don't draw any more of it, but it heads out in this direction. This is where everything starts. And so if we reach negative 55 here, then boom, an action potential fires and takes off down the axon. If we don't, then it doesn't fire. And this is essentially how the nervous system works. As, of course, all those 86 billion neurons in your brain, that's how they work. Lastly, and not illustrated on our screen here, and quite a bit in a simpler manner, we have something called a pacemaker potential. We see the pacemaker potential most significantly in the heart. And so the SA node, but also the other parts of the conducting system of the heart, for instance, the bundle of His. They all, even the Purkinje fibers, they all have some degree of pacemaker potential, ability to conduct a pacemaker potential. Your pacemaker, if everything is healthy, is going to be obviously the SA node, the sinoatrial node, found in the wall of the right atrium, as we'll talk about it in the cardiac system. However, if that fails, then you don't just die. The other parts of the conducting system of the heart can conduct action potentials that allow your heart to beat. So I suppose we should make sure that we are clear on what a pacemaker potential is. We will talk about the different ion channels found in a pacemaker, in pacemaker cells in the cardiac system chapter. However, a pacemaker potential, for now, is simply a bunch of cells that spontaneously depolarize at a regular interval. And so that's why we're alive. That's why our heart is beating, because these sinoatrial node cells continually undergo this repeated cycle of depolarization and then repolarization, depolarization, repolarization. And that's what allows our heart to beat as those action potentials spread throughout the cardiac cells, cardiac muscle cells of the heart. We do have some minor pacemaker potential cells that are found, for instance, in the small intestine, but certainly most significantly, we have the cells that are found in the conducting system of the heart.